Okay, so okay, does anybody have anything to say? No. Okay, what we'll do is since we have actually so we have 3 lecture hours and 1 tutorial. Hopefully, after next week, I'll be able to give you a tutorial problem. I mean, an assignment, and I'll discuss I will give you some hints, okay, about how to solving those problems, and then you need to submit the assignment. I'll give you a date also. I mean, last date. I'll discuss about the last date for the submission, and you have to submit the assignment. So I'm not in a position right now to give you any assignment. I need to do a little bit more, and then I think I'll be able to give you an assignment. Yeah. Yes. Now let us talk about what we discussed last day. Okay, we basically, I mean, it seems we have discussed a lot of things, but basically, okay, so this is just a minute. So this is lecture. This is lecture 4. Okay, so one of the most important concepts that we introduced last day, it is called the entropy, right? We introduced what is called the entropy of random variable. And here, as we discussed, so here we are talking about, yeah, so this is the context. The context is that you have a source, that's an information source, which is modeled as random variable. So X is input, Y is output, or X is capital X is the input random variable, Y is the output random variable, and this is some channel. So this input has possible outcomes, or this random variable has zero with possible outcomes, x1, x2, some xk, and here it is, let's say y1, y2, and some yk, and then we are, yeah, so this is the context, and so this is channel, and guys, should I write a little big, or I mean, it's a little small, okay, because I have changed my iPad. I just will check. Okay, I have to write it bigger like this. Okay. So yeah, so this is the context, and then we first introduce what is called mutual information. Okay, and then from there we define something called entropy. So the basic idea last day we talked about is let x be a random variable. So x be a random variable, and then of course if it is a random variable associated with the probability distribution, of course, so associated with the probability distribution. Meaning we have probability of, this is defined x equal to small x, okay, for all x belongs to x. Okay, not x, but the sample space corresponding to x. So here I can just write this is x sample space. Okay, so this is defined. Okay, then we said, okay, the entropy of x, entropy of x is equal to minus px log px. This is how to define overall x. So you can say x belongs to Sx or whatever the corresponding sample space. So this is called the entropy of x or the random variable. So, and of course we also said like if it is of the form like if px equal to 0, let's say probability equal to 0 for some even, so then it is of course 0 log 0. So in that case we'll assume that 0 log 0 this is equal to 0. This is what we'll assume. Okay. Yeah. So yeah. So
Sir,
yeah,
sir,
please go
sir,
ahead.
sir, please can you explain what is the meaning of self-information? How it reduces uncertainty of happening of X?
How it is?
How it reduce uncertainty about occurring of X?
Yeah.
When
So this we had another interpretation. This we say this is average self information. Okay. So self information is what? So we define which is called mutual information, right? So mutual information means we define I, some AI, okay, and BJ, semicolon. This is AI BJ or AKBJ, whatever we denote. Now this we have to we define it as this. So log of what? Log of P of AI, comma BJ divided by what?
probability of AI.
Okay,
PAI.
okay, PI. So this is how we define what is called mutual information. Now, what is the mutual? This is what is called mutual information,
Sir,
right?
sir, I
Yeah.
have a doubt. Like the entropy is average of uncertainty, and we are
No, no,
here.
no, no, no. Entropy is not average of uncertainty. Why
So,
are you
so,
saying that?
so because see, we are summing over the information of each event multiplied by its probability, and we are summing over all such events. That's what we are doing when we are defining entropy, right?
No, no, no. We are not doing that. These are not events. These are outcomes. Yeah. Go ahead. Individual
In,
outcome. Yeah.
yes, but the self information multiplied with their probabilities,
Yeah.
and that is so so that will sum up to average information.
No, no, no. Here, average mean expectation. See, what is it? What is the difference between average and expectation? How do you do average? Average when you do, how do you write? So if you have some quantities, let's say, okay, any quantity, let's say you have A1, A2, AN, some values. Okay, how do you take the average? What is the meaning of average of this A1, A2,
So
AN?
we will take the sum and divide by total number of
Yes.
elements.
So yeah. So average of this is like A1 plus A2 plus dot 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 plus AN by N. So it is essentially is 1 by N times A1 plus 1 by N times A2 plus dot 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 plus 1 by N times AN. So here now you can assume that if all these things, okay, whatever the numbers, if occurrence of that has probability, let's say 1 by n. That means that if they are all equally likely, then this is like P1 A1 plus P2 A2. P1 is the probability of occurrence of AI, let's say. Okay, so A2 plus dot 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 plus Pn an. So then this is just spatial. So now this is called average. Okay. Now if Pi is they are not 1 by n. 1 by n means they are all equally likely events. Or let's say they are all equally likely outcomes. Okay, 1 and 2 n. Now if these are not 1 by n, but if it is any probability distribution, because let's say a1, a2, an, these are only the possible outcomes. So then this is also called average, but this is actually expectation of this. Expectation means you're doing the average, but here probability values could be different. It need not be equal to need not be equal. I mean, need not be constant, or maybe same. I mean, need not be all the outcomes are not equally likely. So these can say this is expectation of this a1, a2, n. This one, or maybe expectation of the corresponding random variable x, or the random variable x has all possible outcomes a1, a2, an. And whenever I say a1, a2, an, that means they are associated with a random variable, meaning so if you have some possible outcomes, let's say x1, x2, xn, then x1 is associated with the number a1, x2 is associated with the number a2, and dot 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 xn is associated with n. So here average, this is the standard language in probability theory, average instance of expectation. Now you can say here expectation of something. What is that? I said it is average self information. Okay, so expected value of the self information. So you have defined, we have defined what is called self information. I was talking about that. So this is mutual information. So let us first say this is mutual information. This one is mutual information. Okay, this one is mutual information. Now once so this is mutual information. Okay, then what is self information? How did you define the self information from here?
So my doubt was different. So I was aiming to ask, like, okay, we can, instead of saying average, we can say weighted average.
No,
So
no,
the
no. Wait,
the
wait, wait.
weighted.
Wait. Before you, somebody asked the question, right? Let me answer first. Then you ask. Okay. So somebody asks the question. Who asked the question the first time? You only asked? Who asked the
So,
question about the entropy of X?
It is my question.
Yeah. So I'm answering his question. So let me answer him first and then you can ask. Okay. Yeah. So what we are defining here is mutual information. Now, what is the meaning of mutual information in this scenario? Here, let's say, okay, I wrote x1, x2, xn, but here if you can write instead of x1, x2, xk, you have b1, a2, ak, and y1, y2, ik, you have b1, b2, bj. So then what is the mutual information here? This is the mathematical definition of mutual information, but what, I mean, how do we interpret this? I mean, this many bits you can write. So how do you interpret this mutual information? At how much information? So this we also have shown that this is equal to I. Yeah, this is symmetric. That's why it is mutual. So what did we show? AI Bj is equal to what? Bj AI. So that means what do you know if if you know Bj? I mean there are two possible outcomes, Bj and AI. So how much information? So here you see if you know Bj, okay, and then how much you know about AI. Same thing as saying if you know AI, how much you know about Bj. So that's why it is called mutual, because it is equal to this. Now, when you write self-information, so how self-information is connected to mutual information? Hmm?
When the value of probability I given b is equal to 1,
Mm-hmm.
then we define self-information.
Yeah, self-information of what? So if this quantity is 1, right? So self-information of what?
About AI.
About AI. So we define a new quantity called self-information. Self-information of, so this is how we denote it, okay? Or we can just say we had denoted it like this. Just some x, okay? Not a problem. So this is what we have denoted. So this is what log of minus px, right? This is self-information, isn't it?
So,
This is
what is the meaning of this statement?
which
How we
statement?
can say how we can interpret this statement I of x equal to minus log of px?
This
How we can interpret this?
interpret means this is so okay. So first of all, you can say this I, this is a function. So this is giving a value corresponding to x. Now we are calling it a self-information because it comes from the definition of mutual information. Now what is mutual information? Mutual information means if we have two quantities, for example here, if we have two, one is input and is another is output. So if the output is given to you, then how much you know about the inputs, that information, how much amount information. This is how it is quantified. Okay, this is a mathematical definition. Let's say. So we assume that this is definition, that this definition is correct. That suppose this is the value which quantifies the amount of information, okay, which bj provides about ai or ai provides about bj. This is what is the value. Now, if we assume that this is definition, and we also discussed why it could be why it could be a correct definition, because we said if ai and bj they are independent, okay, then what happens? If A and BJ are independent, these two possible outcomes, that means you have no information. So BJ does not provide any information about AI, or AI does not provide any information about BJ. So this value should be equal to 0. This is what we discussed, and we have seen that this is the case because this is just this is the conditional probability. If you use the definition of conditional probability, so this will be equal to PAI comma BJ divided by PBJ. So denominator and numerator will get cancelled. So you'll have log of 1, which is equal to 0. So that means you have 0 bits of information for this, for mutual information about AI and BJ. So if these two outcomes are these two possible outcomes, okay, one is for the input, another for the output. So if they are independent, so that means one does not carry any information about the other one. So if we assume, so that means this is what it measures. Let's say this measures the amount of information which AI carries about BJ or BJ carries about AI. If that is correct, that interpretation is correct, then what is IX? IX is about self, means AI equal to let's say X and BJ also equal to X. That means how much information does it carry, one particular outcome. That is what it is measuring. This is how we can interpret it. But this is just a value, which is you can say bigger equal to 0. This is just a value which you can interpret like this self-information, meaning how much information does it have. So, and we have seen, I mean, we also have explained, see, Px is this, okay? So this is Px, let's say, so, okay. So if this is Px and this is Ix, so what happens? If you increase the value of Px, then what happens to Ix? Ix will increase or decrease. So let's say this is from 0 to 1. Okay, what will happen? Well, what will happen to the value of log? So if probability is more, then what will be the value of Ix?
Ix will decrease.
I will decrease.
Yeah, so when probability is going to, that means if it is less, probability is going to 1 or close to 1, meaning what? It means that it is much more certain that it will occur. Probability is less means much more uncertain. Much more uncertain means it is less likely to happen. Okay, so in some sense, it is measuring also that how much uncertain something is. Okay, because it is in terms of bits, you can say. So this is a value, this is a number, that how many bits. So this is an amount of information, you can say, in the definition, in the interpretation of mutual information, you can say how much information do you have whenever I say X has occurred. Okay, then same thing, you are relating it to uncertainty because some outcome has happened. That means it is all because it was uncertain. Because if it is certain, that means px equal to 1, it has no information. See, px equal to 1, that means it is certain. So there is no information. Ix completely equal to 0. So since x is random, I mean, occurrence of x is random, there is certain uncertainty involved with it. So that has to be connected with the self-information, which we interpreted in terms of mutual information. So Ix, whenever we say that this is, whenever we say that this is a self-information, I mean, how much information does it carry when you say the statement like X has occurred? Okay, so a particular outcome. This is connected with the probability, because probability gives also an idea about randomness. Okay, what is the probability that this will occur? That means how much uncertainty. So that has to be connected with the information. Okay, that how much information does it contain whenever I say X has occurred, and this is a value which measures that. Now, is it clear, or if you have any? Do you understand now?
Yes, sir. Now it is clear.
Clear. Now
Yes.
now what happens is it can be defined for any x, because let's say I throw a die, okay, and in that die, let's say this is a 6-face die. There are 6 faces. It's kind of a die which you use it. Let's say in Ludo. Now, if I say 6 occurs or 5 occurs or 4, whatever it is, it could be an unbiased die, it could be a biased die. So then based on that, you'll have certain probabilities, P1, P2, P6. Now, for each outcome, there is a value associated with it. There is an uncertainty associated with it, and which is, let's say, is measured by the quantity self-information. Now, the question is, now, if I want to make any statement about the entire random variable, that means about the entire die, whatever has happened for any particular outcome, I have a value. Now I want to say, what is the average value? That something has happened. Okay, I don't care about what particular outcome has happened. I want to talk about the average value, average in sense of expectation. So what is the expected value of an outcome? So what is the amount of uncertainty, you can say, or amount of information, okay, or about let us explain this first in terms of uncertainty. So how much uncertain any particular outcome is on average. So that means I have to take an expected value of this quantity Ix, and this is how the entropy is defined. See, this is the expected value of log px. Okay, so this can be said as like the entropy of x is that how much uncertainty is involved about any outcome. Okay, so that's why we are saying it is an average cell information. Second thing is, this is about self-information. Second, why uncertainty? Because each outcome is associated with some probability. That means each outcome is uncertain up to certain extent. So if I am quantifying how much information it is, I am also simultaneously then quantifying how much uncertain any outcome is on average for this random variable. Let's say it is throwing a die. And this is given by this value, which is this many weights. So we are basically trying to measure uncertainty about random appearance of a particular outcome or any outcome corresponding to a random variable x by this quantity, which we are calling entropy. Is it okay now?
Yes, sir.
Okay. Now, Japan Jyoti, you had some other question. Yeah, please go ahead.
Sir, my doubt was related to when we are defining entropy, we are taking the expected value or the weighted average of
Hmm.
information.
Self-information. Yes, yes.
Self-information, right? And so entropy is a kind of average information or maybe expected information from a random variable. Now when we are defining another kind of average of mutual information that we defined yesterday, average mutual information.
Yeah, I think we defined before the, last day, I think. Yeah.
Yes, yes, sir.
Uh,
And
yes.
the thing is, like I'm curious about why some things are while taking upon their average or expectation are treated as entropy, and why some are not. For example, this self information, when we take the expectancy, it is said as average self information, not entropy. Why? So like I'm like it has some different meaning, or like I'm confused about it.
But I am confused about your question. I didn't understand. So,
See,
okay. So first,
some
okay,
things.
what I understood. Okay, let me first try to explain what I understood by whatever you said. So we said entropy about some x, some random variable, and we talked about that this is average. Okay, we'll explore a different way also. I mean, it can be defined. It can be. I mean, you can read different books, and it has to. People have tried to explain it in so many different ways. But anyway, let us say that this is average self-information. Okay, what is happening? Average self-information. This is one thing. Information. Okay, and this quantifies. Let's say. Okay, we'll talk about that. Let's say. Now we also talked about average mutual information. Okay, this is self mutual, but whenever we say mutual, then instead of one random variable, I need two random variables. Okay, so ixy. So let's say, yeah, if I take this, okay, this is how we have defined mutual information, right? Now, this is your question probably, that why we are not calling it. So this is average mutual information. Is that your question, Japanjot?
Yes, sir. So why
Yeah,
it is not some kind of entropy?
yeah,
Like,
yeah. So no, it is. So the question is, we proved, if this is my definition, we related this. So if we go back to yesterday class, so I'll show, today also I will try to derive many things, but just see if we go back, you see here, this is what we explained in terms of entropy. So this is entropy of a random variable. This is the entropy of another random variable. This is the entropy of the joint random variable. The mutual information or average mutual information, okay, of x and y. This is sum of their hx plus. I mean, we'll try to see what is that, but it is kind of, you have an entropy of x. So about some how much uncertain information does this x contain on average, let's say, or in general, that let's say the entire random variable contains, and then plus hy. Okay, the uncertain information about x and information about total information, let's say, from x and y. Now we are subtracting the amount of information which jointly x and y contain. This is what it is. This is how it is explained in terms of entropy. This is how this is. I think this answers it. Does this answer your question? Then I will explain a little more. Is that what you wanted to know?
sir, yeah, partially I accept it. Like we are defining the self average self information in terms of entropy in the last, but like if we claim like this, that like self information, and okay, so when there is a term self information, then only we define entropy. Okay, okay, sir.
Okay, so this is how it is related. The mutual information, the average mutual information x and y. This is exactly equal to the information. How much information does x contain, y contain? Sum it up. This is the total information, let's say, and subtract what is the joint information. This is how I think we talked about how to prove this. But anyway, so we'll again today try to explain a lot of things where this will appear again. So basically, what I'm saying is you have to understand this. Okay, that everything. So I'm emphasizing on this fact that everything depends on the definition of mutual information, which is defined initially, and from that one definition, you can derive everything. That is very, very important. That means if I want to quantify, okay, that how much one particular random variable, how much information does one particular random variable contain about the other one, if other random variable or any other random variable. If somehow I could quantify, which is here I define in terms of mutual information, then I can build up all these concepts. And once I build up all this mathematical concept, then I can try to relate that whatever new definitions I have created based on my intuition, based on my definition, okay, and how these concepts are related and whether they can be implemented or they can be useful in order to build up another concepts which will be useful for information exchange or information processing. And this is not my theory. This is Sanam's theory. This is how he introduced it, and he had shown that this is how, if we define it this way, then all this definition will follow, and accordingly you will have information exchange using this thing, and you can quantify information. I mean, you can quantify information of a random variable. This is how he defined it. Okay, I just wanted to say that, you see, last day what we I think we all said it, but let us say the question is, suppose you want to relate this. So let's say this hx. Now hx can also be considered as, let's say, mutual information between x and x. Is it true? Can I write h of x is equal to I of x and x? Can I write it?
Yes, sir, we can
Yes,
write.
sir.
Yeah. So see, it has now another meaning. So now whatever I was talking about, that average self information. Now this is now, it is like how X contains information about the X itself. So that means it is the self information. So this is the average self information. This is what I was talking about. Okay. So this is another way of thinking about the same thing. Now we prove that Hx is always bigger or equal to 0. Okay.
So
But we did.
mutual information and average mutual information have the same symbol.
What is that? No. So
Mutual.
when in mutual information we define for two outcomes, you see, AI and this thing. I think we have to, yeah, here you see. So here the mutual, here, sorry. So here you see this under this, and then we take average, then we have denoted as x comma y. So x semicolon y. So you can just go to the yesterday's this thing, you can see. So yeah, this is how we introduce small x semicolon small y. This is mutual information, okay? And then we defined average. Whenever you see, we define average. Then we have written this capital X, capital, because here you are taking the average over all X and all Y. Okay.
Yes.
So that's why this capital X and Y. Is that okay? So here
Yes.
in this, yeah. So here in this course, I mean, notations will play a very big role. Okay. So yeah, so that's why you have to practice a lot of problem to get a grasp about this concept. Okay. And here I'll tell you there is a difference. So that's why I initially said this is a little abstract. Okay. So here, I mean, information theory is a subject. Okay. Where, I mean, in which, like, what I want to deal with is basically an idea to let's say mathematicize an idea. Okay. Which is idea which is intuitively okay. Okay. Intuitively okay in a sense which is very, very intuitive. We do not understand what is the meaning of information, but we want to derive a mathematical formula which should interpret information. So there is a big gap. So sometimes what will happen is we have to assume that something is true mathematically, and then we have to go ahead and see if that is true, what is its implications. Okay, whether if that definition does not immediately imply anything, okay, later on it has some implications, and later on you will see that this can connect to many other things. So that's why possibly that original definition was correct. So this is the way we will go ahead. Okay, and there will be a lot of things which will be little abstract, and abstract in a sense that it follows, it may not have any immediate meaning to you, but it is mathematically correct. So whatever it is trying to say, we have to understand from that definition or from that derivation itself. Okay, so every time you may not you may not interpret what is the meaning of this relation or what is the meaning of this definition, but we'll go ahead and see like how this can be useful to derive other concepts, and from there we can make little sense about what you originally started with.
Sir, I
Yeah,
have a doubt.
yeah.
So I was curious about the thing, like as you were saying, like these definitions, we have to believe in them and then try to see what they mathematically imply to
Mm,
check their correctness. Now the thing is, the Shannon come with the person that first came with this idea. Like
mm,
he must not have started from the definition. It must be something different from where he like came back to defining like this is explicitly like can define information.
mm,
Otherwise, like we can start from many different definitions
mm,
and try to see the implications, and like
mm.
how we are so sure like this definition of information is so exact, or maybe like there might be another way of defining information that is more appropriate than this one. Like how, like what is the reason behind defining such an expression?
Yes. So that is a good question. So the thing is, this is in principle it is working. I mean, if this is the way, so because we just have began the course, okay, there will be a lot of concepts we'll be defining, and we'll see all this communication theory. So his paper title was the mathematics of communication. So here we're just the information. So but you need to communicate the information, okay. So his theory works very well in practice. So that means whatever way he has quantified the information, that is correct. This is one way to say it. Yes, there may be other definition of information, and people have generalized it original definition information. That is possible. Nobody is denying that. But the thing is, if this is the way, if you define information, then it makes sense because it has practical importance. So, I mean, this is how it happens. You can have other definitions also. That is not. I mean, you have a lot of entropy definition of entropy. So this is just one Shannon's entropy. You can see Thales entropy. There are a lot of entropies because many people define things different ways. But one thing is constant, which is the property of log. Log is a function, okay, which everybody has used, but for different ways. Okay, I mean, but Shannon used it for the first time. But log is an interesting function. I mean, can anybody tell me why log was used for the definition of mutual information here? What is the property of log that is being used here?
One gives zero, like when the value is one.
Okay, that is one thing. Value of log of 1 is equal to 0. Except that, do you find anything else that log could be used? Because that property of log, it could be a useful idea to use it for the information. What
Convert
is the
multiplication to addition.
that why that is important here?
Uh, if we have like 24 switches, so we have the information is 2 to the power 24. In that case, if log 2 base 2, that information can be saved in 24. Memory need required will be less in case of log for the storing information because it converts multiplication into addition.
Okay, this is a textbook answer. I mean, most of the textbook, this is what is written that multiply, it will convert multiplication into addition. But the question is, why does it do it? I mean, here in these formulas, why did you use this fact that multiplication? So whatever you said, this is also a little bit intuitive from a particular example. So here we said we are talking about bits. That is not a problem. We said what is bit, but it actually does not imply what is the like number of bits recurring. That's what is happening. Yeah. So we just said, okay, let us write it as bits, and then I gave you an example that if we have 2 to the power n number of this, which is you are correct for that particular example at least. So 2 to the power n means what? So 0, 1 to the power n, right? 0, 1 is the last possible alphabet. So 0, 1 to the power n. So this is a multiplication, and from where we get m bits of information, and that is precisely what you said. But that is a story of a particular example. But why did you use this fact that some of this it converts product into addition, and that's multiplication into addition, and that's why it is important. But why did you use this fact? Okay, by the way, okay, there is another
Sir,
thing called
one more thing we can
hmm,
actually see is that in
So
the log property is very important, because when basically we are finding P of AI, and it is basically more than P of AI given Bj, this tells us that if we get that if we know that Bj has already happened, then the information of happening of AI is even lesser than what it was normally. So this gives us even lesser information than what we had initially. So it basically tells us that because of the log function, the thing comes out to be negative. So any information which is negative means it does not make sense. So in that way, the log function is very useful.
no, you cannot say it does not make sense. If this does not make sense, then the definition is invalid.
No, I mean that
Yeah.
negative information is not useful for someone who is receiving something, or maybe it's useful, but uh, we cannot. The uncertainty becomes more. That's what I'm trying to say.
So okay, we'll talk about it more. But does anybody want to say anything else about that?
sir, I have a doubt. The thing is, if like I was thinking, we have a if we are defining the information using log, then we have a problem that it might come out to be a negative number. That is very impractical. So what I was thinking, and like you were suggesting, like the log is very important in the sense we can like it has some nice properties. Some get converted into multiplication and all. The thing is, so we have two branches of log. One is from 1 onwards, another is from 0 to 1. So what I was thinking, what if I'll make it as a function. I will switch that function from 0 to 1 by multiplying it throughout by negative. That way the information will be positive always, and we have this property like the nice property being saved also, and the information will always be positive. So why not such kind of things are being used?
Yeah, because we have not reached to that situation where we used amount of information. We just defined what is information. So I cannot explain that right now. Okay, where this will be used. In fact, I told you that I'll give you a, let's say, workable definition or workable meaning, or let's say like how do I explain it? I mean, a thing. I mean, what do we mean by entropy? That I will explain in terms of an example where where, where it gives you an idea that how it works in practice. But I have to do that only after introducing coding. Okay. So here we have just introduced different we have just introduced some definitions. We talked about some definition, but we did not apply any definition to do anything. Now the thing is, you can define information in different many ways. I mean, you can propose definition, other definition also. But the question is, you can use that definition from a philosophical point of view. That maybe it could be the definition of information. But the question is it useful? Okay. Now, if I want to answer that question, I need to build up the theory of coding where it will be used. So I have not done that. So let us wait for some more days. And then once we implement, once we discuss the idea of coding and we relate to information, then probably you will see that whatever you propose, the definition of information, whether that will work or not for the case of implementation or for the case of communication, or how much that will be useful for the case of communication or interpretation of coding, or what the entire theory of information and coding. And I did not say that log is used because it makes multiplication into addition. Somebody else said, and I said in many books this is what they say. But the question is, did you use this fact here? So yeah, I mean, for me, for like, if you ask me right now, I will not tell you what I understand about why they have used the definition of log. But let's, because I have to develop some other things also. But for a mathematician, this is always correct. Correct in a sense, somebody has refined it. So let us find out what it means. Okay, this is how it goes. So let us find out so what it means, so what it implies, and then we'll see whether that can be the original definition can be modified to make it better or to develop certain things on top of whatever has already been defined or not. Okay, so if something is something someone has defined, let us go and study it and then see what it implies. Yeah. So my proposition is you can define anything you want. That is not a problem. But the question is whether it is meaningful, whether it has whether it is useful to implement, or whether it is useful to uh, to let's say relate something which is important. That is what is the thing. So you can have your own definition. I have no problem. But the thing is, here in this course we are defining Shannon's entropy, or let's say Shannon's information theory. So we are discussing the way he has defined. Now the question, like Japanjot asked, why did he define it this way? Okay. Now he is not no more alive, so we cannot ask this question to him directly. We can only speculate why possibly he has defined it. And one way to understand this is that this definition works. That's why probably he understood that this is the way to define it, because he is the first one to define it. Okay. So he probably had done, because he was also was working with the coding in, so he was he participated in the Second World War, was doing something. So probably from that his work, he has some idea, and that's how he developed this idea. Okay, so that's the thing. I mean, he must have understood something, and then he defined it something. But I don't know what it is. But we can only speculate from what he has defined from the, on. So if we discuss that and dig it out, like what is the meaning of that, and what does it imply, then we can possibly get to know why he has possibly defined it. Okay. So any other question? So Japanjot, you can define whatever you want, but the thing is, once you define that, then the question will be rest of the things also you have to do. Okay, I mean, whether that definition is a good definition to relate other things, or maybe the way it works, this definition has been useful for the design of coding, let's say, or for the design of communication system, point-to-point communication system. So whether that is helpful or not, we'll talk about a lot of things actually in this course based on these definitions. Okay, we'll have a lot of things, a lot of bounds about this, and the main thing we said about, there are two things, two ideas. One is entropy, another idea is channel capacity. Okay, channel capacity will give you, set you a bound, and this is all definitely, I mean, these all concepts are built up based on these definitions. So yeah, and then we'll see whether this definition works there or not. I mean, if that is the sense of channel capacity, whether, I mean, how much information you can communicate or you can transmit through an unreliable channel. Okay, he set a limit, and the question is whether that limit practically that's a valid limit, and it is found that yes, practically that is a valid limit. So this is like directly from math to application, which you can see if you can possibly implement. You can see that this is what is happening. Yeah, and not only that, this has another meaning to something called quantum information theory, because I told you that. So this man Shannon is called the father of information, and von Neumann is called father of computer. Okay, so this is von Neumann's idea to call it entropy. But the thing is, quantum entropy came first in literature, and after that entropy came, classical entropy came. But the thing is, when you go to the classical to quantum system, so then there is I would say smooth exchange of ideas. Okay, or quantum to classical, there is a smooth exchange of ideas. So which makes it more prominent that this is the right concept to define information. Because quantum system means this is close to reality, close to nature. You can say as of today's literature. Okay, today's physics, let's say. Quantum mechanics could be the most close theory to nature. Okay, how to explain natural things, let's say. Anything else? Okay, another thing what I wanted to tell you that time is that, so like I was talking about this log. mm, so many people have investigated time literature. Will say they've tried to develop theory. Then instead of log, so log has a property. Okay, now you assume any other function which has these properties. So can you create an axiomatic definition of entropy, or let's say a theory which can be called probably axiomatic information theory? That is still there. Okay, so I mean any function. Okay, so if some function, any function you can define. Okay, if it satisfies some axioms, some properties, then we'll call that as entropy. That is also possible. Okay, so it's a generalization of log. That way you can think of. Okay, axiomatic information theory. That is also available in literature. You can just search in Google. But we are not concerned about that. We are only concerned about Shannon's entropy. Shannon's information theory. Okay, now the second question is okay. So okay, so what we're yeah, we are still talking about information. Sorry, entropy. So sometimes that's why, since it is related to, as I said, like according to my interpretation or according to my understanding of Shannon's interpretation. What is this? Oh, okay. Yeah, that is good. Okay, so the thing is, we have related the idea of mutual information or self-information with entropy. In fact, we define entropy using self-information. That's fine. And then also we said, okay, whenever you say something is a random variable, then there is an amount of randomness. Okay, so whenever we say that, oh, so whenever we say what is it? Okay, so whenever we say random variable, so we can also say there is an amount of randomness. Okay, we do not know what is random, by the way. Okay, so it is not a probability theory class, so I'm not talking about much about this. But actually, we do not know what is random. Whenever we say random, it means in the sense of probability only. Okay, like probability as a model, and we want to quantify randomness using that model. We want to explain that we explain uncertainty using this particular model. So there is an amount of randomness. Okay, that the random variable possesses. Okay, let's say like that. So random variable possesses. I mean, everybody should agree with this part at least. Okay, so possesses. Oh. Okay, pause. So that means whenever I am defining something related to the random variable x, so it has to be related to randomness. Now, since here I'm talking about entropy as something which is related to amount of information or self-information, average self-information, that means it's somehow related to the amount of randomness. Okay, amount of randomness associated with the random variable. So it is fair to call now that entropy, okay, so randomness means you can say uncertainty. Okay, so you can say that entropy measures, okay, measures uncertainty. So this is safe to call. I did not say this correct, but I said it is safe to say. Oh, whatever I did. Uncertainty. So this is safe to call. Safe to say. Okay, that this is what it is. By the way, entropy, say we are talking about random variables where everything is finite. Okay, so yeah, so we used a, so if we just go back to the definition, so it is some exponents. Okay, so Let me, so in some books you'll see this x, mathcal x, or something, some this kind of x is written to mean that sample space. So then it is very easy to identify. So this is same thing as a sample space corresponding to x. So yeah, px, okay, log px, okay. So it is another way to call, if you call, if you, I mean, this is another way to look at this thing, that if you think of that this is a function of px, okay, so this is a function of, so this is a log of the random variable x, okay, then also it can have other interpretation, okay, this is another way to look at the same thing. Yeah, so whenever we say the number of alphabets or number of sample points is finite, so this is always finite. But if, because I said x is a discrete random variable, but if discrete random variable, so number of possible outcomes could be countable infinite as well, and in that case countable infinite, and in that case countable, and in that case this sum is an infinite sum, so this is a series. So then entropy exists, means this series has to converge, okay. So then the question is, does this series always converge? Okay, so then, and that's a bigger question, okay. So that means whether this is a valid definition or not, okay. Does anybody have any clue whether this will always converge, whatever a px we define for any sample space which is countable infinite? Will it always be finite, or it need not be finite as well? I mean, my question is, can entropy of a random variable be infinite? This is not a finite number, let's say. Is it possible? And theoretically speaking, this is possible, okay. That, so this is, let's say this is my example, or I would say entropy could be, I'll not do the calculation, but I will ask you to validate this. Entropy could be infinite. Just check whether it is true or not. So let me define a random variable then. Okay, so let us say this alphabet is sample space. Let me say this is sample space. Sample space is like this. 1, 2, 3, whatever it is. Sample space is a set after all. Okay. What is it? Whatever it measures, I don't care. Okay. So, or what is the corresponding experiment? I don't care. And this is a sample space. Now let me define a probability. That probability of I, or let's probability of J. This is equal to uh, let's say something like this. J plus 1 log of 2 log j plus 1. But anyway, let's say it is like this. There is a let's say square of this. So I'm manufacturing an example where it will be infinite, and let's say I have some c, some constant, and the value of c is decided by the fact that this is a probability distribution, okay, and c is a constant where c is a constant whose value is decided by the condition sum of pj is equal to 1 or all j. So j means j equal to 1, 2, 3 dot 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 or all j. So from that condition we'll get the value of c. So then calculate the entropy of this random variable associated with this border distribution. Okay, find it out. What is that? Okay. Okay, so this is sort of, oh, another thing is like, okay, there are many small things. Yeah. Somebody wants to say something?
Sir, I was thinking, what if I define it as 1 by 2 power j?
Yeah, you can define
The-
and see whether that
Then
is finite or not.
every term will be 1. So it is sum over n, where n tends to infinity 1.
Yeah, you can do that. So yeah, you can do that. I mean, there are many more, but I'm just giving an example. So, and then another thing is this whenever I say entropy, okay, so I can relate, so x, which is sum of px log x. Then I can also say, okay, this log has a base. So any base, let's say some a, then I'll write it that to be a, depending on the base. So I have something here. Okay, this a, hax, it means the entropy with base a. And we can have a to be bigger than 1, not a problem. So we can write it as a is bigger than 1. And then if you want to calculate, then entropy corresponding to the other base, some b, okay, then what will be that? How this will be related? For example, if you want to calculate this entropy in terms of bits and in terms of nets, so how they will be related? So then you can find just simple proof that this will be this times h of ax. Okay, this is homework. This is homework. Okay, that this is also a now let us just check one example, a very silly example of C. That because not a silly example, but very small example, but it is important example. So why is it silly? Because it is very easy. So let us consider a random variable x, okay, and let us calculate its entropy. Oops. Yeah. So let us say x is a random variable. What is it? X is a random variable, and let's say it is just it explains the tossing of a coin. Okay, that means my x could be head and tail. This could be my head and tail. Okay, but let's say whenever I write sample space, instead of h, I will write it to be 0, 1. Okay, 0 or 1. You can write anything, a, b, it doesn't matter. Anything. By the way, so whatever way you define your random variable, okay. So what is the random variable? Random variable is like the sample space to R. This is the function, right? Associating. What is that? This is to R. So associating H, let's say here, head to some number and tail to some number. So head, I said here 0, tail is 1, but you can also consider head to be some number A like 3 and tail to be equal to 5. Okay. But the amount of uncertainty, you see, that should not change. That means entropy should not change. Entropy should not depend on the value of this function. Okay. So entropy only, that's why entropy only depends on the probability, not any other thing, not on any other thing. Okay, so how to define it? The random value doesn't matter. Okay, it only matters about the probabilities of this individual outcomes. Okay, and if we have, let's say, probability of success, let's say head is a success or tail is a failure or whatever it is, doesn't matter. So let us say if p is the probability for, let's say, probabilities of 0 is equal to, let's say, p, and probability. So this is the probability distribution. Probability of 1 is equal to, let's say, 1 minus p. So if we consider this very simple example, then what is the entropy of x in terms of bits? So this will be what? P times, so summation px log px, and then this is minus overall x. So here x equal to head or tail or 0 or 1. So it is minus p of 0 log of p0. Okay, minus p of 1. Sometimes my pen is not writing. 1 log of p of 1. So which is what? So minus p log p minus 1 minus p log of 1 minus p. So this is my entropy. And if you draw this entropy, I mean if you draw this function, okay, this will be a function of p, because probability of success or probability could be anything. So p means if it is a biased and if it is an unbiased coin, then p value is half. Probability of getting, let's say, 0, or if the outcomes are equally likely, then this is half. P is equal to half. So then what we could, and then if we just draw that based on probability, how does this look like? Then you will see that if I consider this to be equal to P and say 0 point something, let's say 2, 4, 6, okay, and let's say 0 0.8, and here let's say 1, 1.0 or 1. If this is the probability, then you will see that it will take a shape like this. It will, oh, it will take a shape like this. So let's say this is 1, okay, and this high value will appear here when it is 1, 0.5. So this is HP, or let's say H. So let me write this called, it is a function of P. Let me write it as HP. So this is HP. So this is entropy. Okay. So how then there is a question. Okay. I mean, that is a bigger question, but this is a question like how entropy depends on probability distribution. Okay. As a function, how does it do here? What kind of function is it a convex function or concave function? So because here this is very simple, because here there is only one value P, but there can be multiple values of P. I mean, okay, multiple values of P means, so if there are multiple or more than, let's say, I mean, there are many random sample points, there are many possible outcomes, then it need not be defined in terms of a single parameter P. Okay, there may be multi-parameter, and then this will not be just x-axis, but it will be some x, y, z, depending on how many parameters you need to define the probability. So then the question will be, so then there will be a vector. Okay, so here I can just draw it just using two dimension. Okay, because there is only one parameter, but there can be multiple parameter. Okay, and then accordingly I have to draw it. So then in that case my question would be, I mean, what is the property of the entropy as a function? I mean, function on the probability distribution. Okay, because it depends on the probability distribution. So what kind of, how does it interact with probability distribution? So meaning, set of all probability distributions. So if you consider, okay, there you may possibly define addition and something else. Okay, so we'll see what can be done. But so the question will be, how does it behave? So here, at least if we just plot it, okay, on depending on P. So sometimes also I must say this because we'll be using later on some examples. So this is called binary entropy function. This for this particular special random variable, it's called binary entropy function. Okay, so this HP, or sometimes people write H2P in different books. Okay, but this function has okay, a very nice thing. So is it concave or convex? So what is it?
It is concave.
Okay, so from this example, we can have just an observation. We'll see in general what can be done. That entropy for this particular entropy, okay, for this example, entropy, let's say, is concave. As a function, it is concave, continuous, and takes, and the maximum eigenvalue, not eigenvalue, the maximum value, okay, occurs at p equal to half. But p equal to half is very, very important here, because p equal to half is like completely unbiased. There is no bias. Okay. So all possible outcomes are equally likely. Then the maximum, you will get the maximum entropy. That means then it is completely uncertain. Okay, this is the maximum entropy possible, the maximum a possible value possible. Okay, about this random variable. Like if p equal to half, that means probability of occurrence of head is half, tail is half, and then it contains maximum information. This random variable contains the maximum information because it is completely uncertain. If you are going to toss, you don't know, you are not sure whether it will be tail or head or tail. But if you distort this power distribution a little bit, let's say you make pt the value 0.8, that means 80% chance that it will be head or it will be zero, then the entropy drops. Okay, the uncertainty drops because there is 80% chance that you are going to get head. So that means uncertainty, the level of uncertainty, okay, reduces. Okay, compared to p equal to half. Similarly, if you say probability equal to zero point 0.2, okay, that means probability of getting tail is 0.8. Okay, so in that case also this amount of entropy reduces. Okay, so yeah, this is just an example to understand entropy, but okay, I mean there are many things we can read, many other things, other books where they have tried to define this thing. And then we said, okay, we can talk about also joint entropy whenever let's say the function is, I mean the random variable is not one single random variable, but let's say pair of random variable. In fact, we define joint entropy for a tuple of random variables. Okay, in fact it is a random vector. Okay, so this also we talked about last day. So we talked about entropy of a random vector instead of a
Sir,
random variable. Yes.
sir, sir, above example, random variable is special name like Bernoulli distribution.
The distribution is Bernoulli.
Yes, sir. Because in only two outcomes, success or failure, so we can say this particular random variable is Bernoulli random variable.
Yes, yes, yes. It is a Bernoulli random variable. Yes, yes. Correct. Yeah. Okay. So we can also define entropy of a random vector. So that means if we said we can sometimes do it like this, instead of only one random variable, we can have n number of random variables. Okay. And we also talked about an example where this could appear. We'll see later also that you can have cascaded random variables. So in fact, when you have cascaded channels, okay, then you can have this kind of a situation. You have a joint random variable or is have a random vector. And anyway, you can also define this thing similarly. So I'm not defining it again. It's because it depends only on the probability. So you can the same definition, okay, minus px. So instead of px, here it will be p of p, p of x1 x2 xn, okay, and then log of x1 p of x1 x2 xn. So overall x1 x2 xn, these are the sample points. So this is how we can define it. Okay, same thing. Okay, now let us go back to our example of this uh, channel, okay, and see whether we can get some more information about this definition. Okay, whether it can this quantity like entropy can have some other interpretation from the point of view of a channel. Okay, because we also defined, okay, so this is also what we defined last day, which is called conditional entropy, right? We also defined what is called a conditional entropy. Right? We defined what is called H. So okay, let me write it first. Conditional entropy. Because I said, okay, entropy is kind of a function of a random variable. Okay, random variable could be equal to like a conditional random variable. So then you can have like this H, so any kind of random, so H, and then you can have something like, let's say y given x. Okay, So how did we define it? How did we define this thing? Quantity, conditional random variable. Sorry, conditional entropy.
Which is equal to entropy of joint minus entropy of X.
Okay, this we proved, but how do you define this in terms of, let's say, a sum?
Negative
This is
summation over
this average value of something, right? What should be this one? Sum of something, right? What is that?
Sum over xy, px comma y,
Mm. Then
then I of x y given x.
I of y given x. So it's a here whenever I define this, did I say? Yeah. So this is actually ix. Okay, this is actually ix. Self information. So then the question is, when you have conditional random variable, so then how do you do it? Okay, somebody said something, so let us write that. Mm, yeah. So I mean, we defined it yesterday, but let us say, so what is that you said? Sum of pxy, then
I of y given x.
I of y given x. I of y given x. Okay. Does everybody agree with this definition? We defined it yesterday, but just let me just check. Oh, there will be minus. Oh no, everything is okay. So does everybody agree with this definition? What it means? Okay, nobody is saying anything. It means everybody is confused. Either everybody understands or nobody understands. So let me write it this way. Let me write it this way. We defined it yesterday, by the way. Anyway, so now let us relate to this concept with our channel. Okay. I mean, it can be defined in other ways as well. Can anybody say? And then we'll prove that whether this would be equal to anything else. Does anybody have other definition to quantify this? What is the entropy of y given x, given the random variable x? What could be the possible definition? What could be a possible definition here? Okay, what is y given x? What is the meaning?
That is
minus log p of yx.
Minus log.
P of y given x.
Okay. Yeah, so this is fine. So this is our definition yesterday. Okay. Okay, now let us see what it means when we talk about conditional entropy, what it means in terms of this channel. Okay. So what is a channel, by the way? We talked about that. So let's say I will not every time write like this. We'll just sometimes write like this. This is X and this is something. Okay, this is the channel. Okay, or maybe we'll write something like this way. So we'll write that X goes and there is a channel and then this is the output. And how is the channel described? Recall my example of binary symmetric channel. This is given by a probability distribution. Okay, conditional probability distribution. You recall that I had this, let's say 0 a1 a2, and I had this b1 b2, and then we said okay, this to this. Okay, this is what, and this to this is what. So this, the first arrow, the horizontal arrow, it means there is a chance that B1 will be received when A1 is sent. So this is probability of getting B1 given A1. And this one, this slanted arrow, it means probability of getting A1, sorry, B2 when A1 is sent. Similarly, I can have this one. Okay. So this will be probability of getting B2 when A2 is sent, and this is probability of getting B1 when A2 is sent. So this probabilities actually induce uh, some randomness, or induce some kind of error, or there is a chance that there is or there's something called noise. Okay, so that's why this probability distribution induce this noise. So sometimes there is something called white noise and other thing. So let us say sometimes we'll denote this to be equal to some W. Okay, W, let's say Y given X. Okay, because this is what it is. So this is probability of Y given X. Now once you fix X, so then this will define a probability distribution, right? Because this this X is fixed, for example. You see, we had seen it last day in the example of binary symmetric channel. Then there are two options. One is B1 and B2. That if A1, if A1 is transmitted, then either in the receiver's end, either B1 or B2 is received. Okay, so that means if P B1 given A1 is the probability to get B1, and P uh, B2 given A1 is the probability for the other thing, and sum of these things must be equal to 1. Okay, so that's what we said. So whenever we fix X, then WY given X for all Y. Okay, that gives a probability distribution on the output variable, because it is defined on B1, B2, BK. Okay, does everybody understand what I said? Or nobody understands? Okay, what you said. Say, if you don't understand, please speak up. Okay, if you don't say anything, then I'll not understand whether you have some questions or not. So okay, so let me elaborate this, because first time we are I mean, this is the second time we are discussing the same thing. So let's say, let me give it much more, explain a little bit more. So let's say this is A1, A2 dot 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 some AK, and this is B1. Okay, let me dot like this. This is B1, this is B2, and this is dot 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 some BJ. Okay. Now when A1 is sent, A1 is being transmitted, then what happened? Okay. Yeah, so some BJ. Now see, once A1 is transmitted, okay, then either you will receive B1 or B2 or B3 or BJ, one of these things. So that means this is what probability to get B1 when A1 is sent. This is probability to get B2 when A1 is sent. and so on. This is probability for Bj receiving Bj whenever it's sent. Now, since this one of these must be obtained, I mean must be received, B1, B2, Bj, so that means, and these are the corresponding probabilities, that means this will define a probability distribution on B1, B2, Bj. So this induces, because what? We are defining B y given x for all y. Y is equal to, let's say, B1, B2 up to Bj. Okay. So that means this is a probability distribution on y. Okay. Similarly, A2, if you fix A2, then corresponding to A2 also you will get a probability distribution of this. Does it make sense? Other way of saying is,
Yes, sir.
okay. Okay, so I'll not explain more about that. Okay, so basically what is, so let's say my x, oh, what is happening? Yeah. So my x, let's say, why this bar is coming? X equal to, let's say, A1, A2, AK. So this is my alphabet. Sometimes we'll call alphabet also the sample space. And let's say this y is equal to, let's say, B1, B1 dot 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 Bj. Okay. So then what we are saying is that then what we are saying is that if we consider this as a channel, so this W, okay, this describes the channel, then what we are saying is that sum, if you take W y given x, this is equal to 1 for any x over all y. This is what we are saying. Okay. And this y w y x, w y given x, this is what this conditional probabilities, define the channel. So what is the meaning of a channel? Channel is nothing but a set of conditional probabilities. Okay, that's it. Now see here, we are talking about two random variables, x and y. So what is the joint distribution here? Probability. So I could have said this thing here as well, like here when I said this. This is what? Say this is probability of getting B1 when one is sent. And so there is something called probability of A1 comma B1. What is our probability? It's the joint distribution. Okay, joint probability. And there is one more thing, PA1, and there is one more thing, PB1. Okay. So PB1 is actually this, PB1 given A1 when A1 is fixed. So due to the definition of due to the definition of conditional probability, what do we have? We have the joint distribution, let's say xy, which we denoted as this. Okay, this equal to px times w. Instead of writing w, we can always write p also. Okay, it is not a problem. But since it is a channel, it is related to channel. So that's why we're writing it, giving it a different notation. Otherwise, we can just say it as p y given x, same thing. Okay. So this is the joint distribution. So this gives the joint distribution of xy. Okay. So from here, then we can also define. Then we can define a probability distribution. Probability distribution. Okay. By the way, once we get this joint distribution, from using this joint distribution, we can calculate joint entropy. Okay, joint entropy, that is hxy. This we can calculate, or just hxy. Sometimes we write this hxy. That's it. Okay, the joint number. You can calculate this. Further, we can also define a probability distribution on y. Okay, this is what I said, for distribution on y. Okay, which is what given by all this. Can you hear me, guys?
Yes,
Yes,
sir.
sir.
Okay, as follows. As follows. So we can just say probability of y given y is equal to sum over x px pxx times w y given x. Okay, over all x. So this also defines the probability distribution on y. And then we talked about conditional probability yesterday, a conditional entropy yesterday. Then we can now define the conditional probability. Okay, so if we have a let's say working definition of and working meaning, let's say, okay, of or an interpretation of what is called conditional entropy in the sense of a channel. Okay, so if we fix the output input, if an input x is fixed, okay, then the output has a probability distribution. Output y has the probability distribution. We just defined it before, y given x for all y is in, how did we denote it? Uh, y script y. All y is this, okay? So then, what is the entropy? So then now say, we can now define the conditional entropy, okay? So y given x, this is why it is required. So when x is fixed in the channel, okay, how much uncertainty is there about the standard variable y, okay, about this, average self-information about this, when x is being transmitted, okay, then I want to measure, quantify this. So that is the conditional entropy here. So this will be what then? This will be just the definition. Y, just the definition of entropy. This y and probability, which is here y given x, and then of course log of w y given x. So now if I take, this is for a given x, given x. Now if I take the average for all x, what is the average entropy? Okay, kind of a thing. So expectation of this entropy, okay, with respect to the entire distribution pxx. So that will give me this. Okay, so now if we take, so I have to write everything, otherwise I may not write also, but anyway. So if we take the expectation, take the expectation, the average or expectation, because average is sometimes confusing term. So expectation over the input distribution over all, okay, over the distribution of x, okay, then what happens? Then we have this quantity h y given x, okay, which now you see, which what should be the definition now here is the average over x. So that means we are talking about with the probability x and h y given x over all x. Now see, yesterday we defined something else. Now my question is it equal to what we defined? Is it equal to what we defined? Like here it will be, okay, let me do a step jump. Is it equal to some minus, this is what we defined yesterday from another definition of condition probability. Yeah, so another definition of this thing, that entropy of a conditional random variable. We just defined what is called this entropy of this conditional random variable. But here now we have a working definition, okay, in the sense of the channel. And then they must be the same. So I'm just showing it to you that they are same. So it must be like this. And we said I of y given x. This is what we had defined, I of y given x. So which should be, okay, so then I have to write something else here, not here. This is what we defined. So this has to be this. What is happening? P xy xy, and this must be log of, oh, so the minus will not be here. The minus will not be here. And this has to be log of what? Not to the probability here. This is w y given x. Okay, this is what it is. Now see, from this working definition of entropy or conditional entropy, what should be this step, the missing step? What should be this one? This was the final definition, was our definition from just the entropy of conditional random variable. But here I am doing something which is meaningful in the sense of information exchange, okay, or in the sense of point-to-point communication system. So then what is the missing link here? What is this? What should be this? Here, what is this term? What is happening? Who can tell me?
So we can expand the entropy of y given a particular x. From there, we will have one summation and w of y given x, and we can multiply w of y given x with the probability of x to have probability of
Yeah.
x comma y.
Yeah. So you can write this entropy, definition of entropy, because it is known to us now, because this is what it is. Okay. This is what it is. You just write it down and see, and this is meaningful because we have defined it. Okay. So then if you just write it down, you will see that this is what we did. We said that this should be the definition and this is what it is in the sense of the channel also. So it is meaningful. Okay. It is meaningful in the sense of Shannon also, that this is the correct definition. That whenever we have this B1 A1 A2 AK and B1 B2 BJ, and if we have this conditional probability, this is what it implies. Okay, so this is a working definition. That means this works in the sense of a communication system where we have information or symbols which is being transmitted from an input source to an output source. Okay. Now here is some observation which you said yesterday also, but now we want to check whether it goes, okay, as par with the interpretation of the communication system. Okay. First of all, this is, we always said that this is mm, h, okay, y, x. This has to be bigger equal to 0. Is it correct? I mean, we actually said this is bigger equal to 0, but for that we need that has to be bigger equal to 0, small x. This is one thing which we discussed this thing, and this will be, see that, just check this homework, just check that this is valid from the definition also, or definition corresponding to the communication system. Second thing is, when does it, when is it 0, let's say? When is it equal to 0? When there is no information between x and y. When given x, okay, the entropy about y is completely 0. That means everything is known about y. So everything is certain now. If I provide this information, if I give you x, okay, then everything is known. So there is nothing uncertain. Uncertainty is, amount of uncertainty is 0. So when that can happen? About any, so let's say, yeah, somebody wants to do something?
So when the channel will have no like it will be having no error, like channel will be, how to say, noiseless. So if we are giving A, then the output will be A on the other side also.
Okay, but in the sense of random variable, what does it mean? When can it be equal to
So when
0?
both are independent.
Independent, there are two things. One is, here we are talking about entropy, and there we are talking about mutual information. Mutual information could be 0 when one is independent of the other one. But what about entropy? Entropy means amount of uncertainty, okay, about y when x is supplied, x is given. When can it be equal to 0? See, if they are independents, uncertainty will be same as y, right? Amount of uncertainty, so that means nothing, no information is given to you. But information, amount of information could be 0 only when all information is given to you. That means what should be the relation between y and x? Okay, I'll tell you the answer. But do we have any idea or any intuition?
So when the conditional probability P bi given A is equals to 1 for all such cases. So so
Yeah, what is?
if we have A1 to AK and B1 to BK, then A1 will get mapped to A1. That means probability of B1 given A1 should be 1, and for all other cases it should be 0.
Okay, let me put it this way. Okay, and then mathematically whether you can prove it or not. If and only if there is a function f such that f of x equal to y, that means y is a function of y. Somehow complete information about y is known since x is known. Okay, such that this. So that means we have to show mathematically that if this is 0, then y must be a function of x. And if y is a function of x, then we have to show that this is 0. This is also homework. Okay, you read books, that book which I referred to, you'll see all these things are there. Okay, another thing which we proved last day, okay, is, I mean yesterday, is this h of xy, or x comma y. Okay, this is equal to hx. Can you prove this or can you interpret this in terms in terms of the communication channel or the in terms of the channel? Can you interpret this? We proved this because of the definition. We said okay, this will follow. Just use the definition of all these quantities. This will follow. But what is the meaning of this? In fact, if you want to see a picture about this, so let's say if this is, let's say this is hx, this amount of information about x, and this is, let's say, amount of information about y. Okay, then this particular region can be said about entropy of y given x. Okay, then say this makes sense. Hxy is equal to hx. Hxy means the entire thing. Okay, the entire. I'm not making any shade, but okay, you can make a shade if using a different color. So it's like this. So let's say it is not hxy, the information, okay, amount of information about the joint random variable xy. So it is not equal to hx plus hy. Okay, because there is a overlap. Okay, so this hxy is nothing but hx plus h of y given x. So this is how you can, if you want to see it in a picture, in a Venn diagram, let's say, then this is how you can look at it. Okay, this we have proved. We have also stated another thing yesterday, which is the following, which is said you can have a chain rule. This is also called chain rule, but we proved it, or maybe I gave you a hint about how to prove it, which is x1. So if we have a random variable, which is, or a random vector, let's say x bar, okay, this is equal to h of x1 plus h of x2 given x1. So it is a generalization of this fact. If we have two, we have this relationship, okay, just x and y. So it is hx plus h of y given x. Here it is n, okay, n number of such things are there. And then this will be h of x3 given x1, x2 plus dot dot dot, and finally you have h of xn given x1, x2 dot 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 xn minus 1. So this is the chain rule. Then the question is, if you have a cascaded channels, then you can you try to see what is the meaning of this. Maybe you have 3 channels, okay? So let's say here is x1, okay? Let's say we have x1 here, x1, then there is a channel, okay? And then something, let's say instead of x1, let's say x, and then let's say here I have y, and then again it is through some channel, okay, and then I have information z. Then what I can say about x, h of this thing, h of x comma y comma z, what I can say about this, what should be an operational meaning, okay, of this thing, operational meaning of this thing. Yeah, so what we have tried to do today, whatever we discussed last day, so not everything is, so I wanted to connect this to the digital communication system, point-to-point system, okay, that these are all true in the sense of common sense and in the sense of the original definition. So when we consider the definition, we only consider random variables. So it did not, okay, we sometimes we refer to the this communication channel, but not the sense in the sense of what we did today. Okay, so so the thing is, yeah, so the definition introduced for random variables, okay, so they have an operational meaning when we talk about a channel, okay, at least one example of a channel if you consider, then we'll see that it has an operational meaning. So these are relevant, Okay, and this can be extended to random variable. Okay, and this is what it is. So if you have any other question, you can ask. Then